Okay, now we're going to jump up to topic 5H, and we're doing that. We're skipping some of the examples of equilibrium, only because I know you see a lot of things like acids and bases in 108. And so I'm just going to jump up and do the important things for electrochem. You also see that in 108, but I feel like it's such an important application of equilibrium. And it's always at the end of 108, and I don't feel like a lot of it sinks in because you're kind of tired by that point. So we are going to talk first about ions in solutions so we get a better understanding of how you deal with this fact that concentrations often have to be adjusted for non-ideal behavior. When you're talking about electrochem, you're talking about usually solutions that have a high ionic strength, so there's lots of ions in them, and those ions are really what begin to behave non-ideally. So the most significant, well, ions in solution interact with the ionic atmosphere that assembles around them and affects their chemical potential and mobility. So you've always heard about that idea. If you have a cation and it's in solution, it's going to be surrounded by anions to help balance out that charge. So that effectively kind of reduces the impact of that positive charge. So the most significant difference between electrolyte and non-electrolyte solutions is that there are long-range Coulombic interactions between the ions in the former. As a result, electrolyte solutions exhibit non-ideal behavior even at very low concentrations because the solute particles, the ions, don't move independently of one another. So if you have a cation surrounded by anions or an anion surrounded by cations, that totally changes how things move through solution and therefore how things react in solution. So it's this Coulomb potential that's important. So the charge on each of the ions, the capital Q divided by 4 pi times this is the electric permittivity, which if it was a vacuum, you'd have this not sign on it, but in a liquid, it's actually what used to be called the dielectric constant. And then it's a function of 1 over r, so how far apart the particles are. When we think about an activity coefficient, the activity coefficient is what you'd have to multiply the concentration by in order to get the effective concentration. So the activity. So the activity equals the activity coefficient times the concentration, and of course divided by the standard state concentration, because that's always true. So as something becomes more dilute, as the concentration of J goes to 0, the activity coefficient should go to 1. But anything other than that, the activity coefficient won't be 1. So once the activity of the species is known, its chemical potential can be evaluated from the equation that we've been using that says chemical potential equals the standard state chemical potential plus RT ln of the activity of J. So the thermodynamic properties of the solution, such as the equilibrium constant of the reaction involving ions, can then be derived in the same way as for ideal solutions, but with activities in place of concentrations. So we'll use our equations that we derive for ideal behavior, and we'll make a correction with an activity coefficient. However, to make the connection of the resulting expressions to observations, it's necessary to know how to relate the activities to concentrations. So we're going to go through a theory called the Debye-Huckel theory that is a pretty good theory at calculating activity coefficients. So the first thing you have to realize is if you put something in solution, you get a cation and an anion, you can never measure the activity coefficient of one or the other. It's always an average. So the activity coefficient, if you had sodium chloride, you'd have the activity coefficient to the 1/2. Whereas if you have some other complex salt, it's going to be the P's and the Q's are defined right here. So P So the P is the number of cations you have, and Q is the number of anions you have. So the average activity coefficient is then, I've got it written right here, going to be equal to the charge on the positive cation raised to the P power, the charge on the, or not the charge, the activity coefficient raised to the P power, the activity coefficient raised to the Q power, and then to the 1 over S. So you take the root of S, and S equals just the sum of P and Q. So this problem is 5H.1, where it just asks you, it gives you the experimental value of the activity coefficient of, oh, that's the mean activity coefficient is 0.664, and the concentration is 0.02. Suppose that you knew the activity coefficient of chloride is 0.811. What would be the activity coefficient of calcium in the solution? So we just have to use this equation. So we have the mean activity coefficient is equal to the activity coefficient of calcium times the activity coefficient of the chloride squared, because there are 2 of them, and then it's 1 plus 2, so that's 3, and you get a mean, or an activity coefficient of calcium to be 0.445. You can skip this derivation. It just derives where that this comes from, that you raise each of them to the power of how many ions there are and take the 1 over S root. That's pretty logical, and I wouldn't ask you to derive it, but it's not really a fundamental concept. So the next one is estimate, so this is 5H.2, estimate the mean activity coefficient for the ions in a 5 times 10 to the minus 4 molar solution of aluminum sulfate at 25 degrees. And so we're going to use this equation. Oops, I did not give you the equation yet. The equation is right here. It's called the Debye-Huckel limiting law. So this is a theoretical approach to getting activity coefficients. So it says that the log of the activity coefficient is equal to negative A, absolute value of the product of the charges on the ions, times the ionic strength to the 1/2. So the ionic strength takes into account basically just how many total ions. So if we had other things in here besides aluminum sulfate, we'd have to include those in our list. So we're going to use those 2 equations. So to get the ionic strength, equation is right here. So it's, so didn't write it down. I'll write it down bigger. So it's equal to 1/2 the charge on the cation squared times the molarity of the cation, plus the charge on the anion squared times the molarity of the anion, all divided by your standard state. So we have a concentration of aluminum 3+ of 2 times the concentration of the aluminum sulfate that you put in, because you get 2 of these and 3 of these. So 2 times that is 10. So this is the concentration of the aluminum. This is the charge on the aluminum. So 3 squared plus sulfate is 2 squared, and then it's 3 of those. So it's 3 times 5, 15 times 10 to the minus 4. So our ionic strength is 0.0075. So then the log of the mean activity coefficient is the equation right above that, which says log of the mean activity coefficient is negative A, charge on the cation, charge on the anion, to the ionic strength to the 1/2. So A is just a theoretical parameter, which we're not going to go through where it comes from. So 2 times 3 charge on the cation times the anion, the ionic strength, the 1/2. And I did this problem twice, and I keep getting 0.543, whereas Adkins got 0.77. Go ahead and try to find my error. I'll give you some extra credit points if you can figure out what I did wrong, or if you can confirm that maybe Adkins is wrong. But that's how you could calculate an equilibrium or an activity coefficient. Here's just another equation for a more accurate calculation of an activity coefficient. But notice you have 3 parameters. You have an A, B, and C. And you have to adjust those parameters empirically. So you'd have to measure the activity coefficient and then determine those with the best fit. And so it's not quite as useful as the last one where it's completely theoretical. So as we go through electrochem, it's going to be important to think about activities instead of concentrations, because as this pointed out, even at very low concentrations, ions don't behave ideally in solutions as something like benzene mixing with toluene. Those two might behave ideally, but ions dissolved in solutions don't, so we have to go to activities at pretty low concentrations. You can skip this 5H.3. That's talking about how ions move, and we won't have to worry about that. All we're going to have to worry about is being able to determine what an activity is for a solution in order to relate it to a cell potential. So our last 2 sections deal with the application of equilibrium to electrochemical cells, and we'll do those soon today.